In this video, I'm going to look at the rotational kinetic energy of an object that's rotating around its center of mass. I'm going to use this to lead us to a new concept called moment of inertia. And then I'm going to go ahead and use that to solve a couple of conservation of energy problems involving rotations. So let's say I have some wheel that rotates with some angular velocity omega around its center of rotation, around its axis. And I want to calculate the kinetic energy of this rotating wheel. Even if the center of mass of the wheel isn't moving, the wheel itself is definitely moving, so it should have some kinetic energy. Well, the way I would do this is I would start grabbing little pieces of this wheel. Let's take this little piece right here. I'm just going to take a little chunk of this wheel. Right there. I'm going to say this chunk has a mass m1 and it's a distance r1 from the center of the wheel. Okay, so I can write the kinetic energy of that little chunk there. K1 equals 1/2 m1 times v1 squared. This wheel is rotating around like this. The velocity of this little chunk here is going to be tangent to the circle, and this velocity v1 is going to equal omega times r1. We know there's that relationship between tangential velocity and angular velocity omega. So I can write this as 1/2 m1 times omega squared r1 squared. Okay. Now I can do the same thing with some other little chunk of this wheel. Let's grab this chunk here. It's some distance r1 from the center of the wheel. This is a little mass. Sorry, this is not r1, this is r2. This is a mass m2, and it has a velocity vector here. v2 equals omega r2. Well, the kinetic energy of that little chunk K2 is going to equal 1/2 m2 v2 squared, which will be 1/2 m2 omega squared r2 squared. And let's just do one more. Let's grab this little chunk over here. Say this is m3. This is going to be v3 equals r3 omega, and r3 is the distance of this little chunk from the center of the wheel. Okay, so finally K3 equals 1/2 m3 v3 squared, which is 1/2 m3 omega squared r3 squared. Okay, now if I want to calculate the total kinetic energy of the wheel, I can just sum up all these kinetic energies. K total equals K1 plus K2 plus K3, and so on. Obviously, there are many more than 3 chunks of mass in this wheel. I just picked 3 random chunks, but I have to do this for every single chunk in the wheel. I can write this as 1/2 m1 omega squared r1 squared plus 1/2 m2 omega squared r2 squared plus 1/2 m3 omega squared r3 squared. But you can see each of these terms has a 1/2 omega squared in it. So what I end up doing is I write this K total this way. I write it as 1/2 of m1 r1 squared plus m2 r2 squared plus, and so on for all the m's and r's, times omega squared. This quantity here, m1 r1 squared plus m2 r2 squared, I call the moment of inertia. That's I. Capital I equals, and I can write it in summation form as the sum over I of all of the mi ri squared. I add up all the little chunks of mass times their distance from the center of rotation squared, and that gives me the moment of inertia. inertia. Now, I don't really like this term, moment of inertia. It's a little bit, I don't know exactly what it means, a moment of inertia. I often call this the rotational inertia, which makes more sense. Remember, inertia is a measure of how hard it is to move something. The more inertia it has, the harder it is to get it to accelerate, the more force you have to apply to get it to accelerate. Well, rotational inertia is a measure of how hard it is to rotate something. The more rotational inertia it has, the more torque you need to rotate it. And we'll learn about torque in the next video. That's what rotational inertia really means. But it also it plays a role in calculating kinetic energy. So our total kinetic energy, I can just write as 1/2 I omega squared. So if I look at this I here, this rotational inertia, is kind of like mass. It's kind of like mass. It plays the same role in this equation as mass does in the equation for translational kinetic energy. And this omega is like velocity. It's an angular velocity instead of a linear velocity. So this looks a lot like 1/2 mv squared, except I replace m with I and v with omega. Okay. So I define this moment of inertia I. It equals the sum of all the mi/ri squared for any collection of point masses. And then once I know what I is, I can always find the kinetic energy of a rotating object. K equals 1/2 I omega squared. Now, for a continuous distribution of object, like any solid object, like a rod or a hoop or a sphere, I can't just do a discrete sum of point masses. I have to actually do an integral over the whole mass distribution. Now, we're not going to be doing any moment of inertia integrals in this class. Instead, we'll just look up the moment of inertia for different objects in a table. So I'm just zooming in real quick. Different objects have different moment of inertias. You have to do integrals to calculate these moments of inertia. But for all the basic geometric objects we're going to deal with in this class, you can just look it up in a table. And I've zoomed in here so you can see what these moments of inertia are. For a hoop, the moment of inertia I just equals the mass times the radius squared. For, say, a thin rod about an axis through its center perpendicular to its length, so that would be like a pen rotating around its center. Moment of inertia is 1/12 m times L squared. For a cylinder rotating around its central axis, or a disk, it's just 1/2 mr squared. A solid sphere is 2/5 mr squared. A hollow sphere, a thin spherical shell, is 2/3 mr squared. So these are all different formulas you're going to use, and this is just a table I took from your book. All of these formulas in this table give the moment of inertia of an object around its center of mass. Now, the moment of inertia of an object, it's pretty easy to see that it's going to change as I move the center of rotation of that object, because the distance of all the little masses that make that object up from its center of rotation change if I move that center of rotation around. So if I've got this pen here, I can calculate one moment of inertia for this pen rotating around its center of mass. What if I want to find the moment of inertia for the pen rotating around its end, like that? Well, I can use what's called the parallel axis theorem to figure that out. So the parallel axis theorem says that the moment of inertia around any point, any axis parallel to an axis running through the center of that object, can be found from its center of mass moment of inertia, I com, plus mh squared. Okay, h is the distance from the center of mass to the new center of rotation that we're looking at. So for example, this pen here, it has a length L, and its center of mass is right in the middle. It's got a mass m. Well, if I want to find its moment of inertia about its end, right here, well, the distance from the center of mass to that end is h. And so I can use that along with the parallel axis theorem to figure out the moment of inertia around this rotation center? Okay, first of all, the moment of inertia ICOM for a thin rod like a pen is 1/12 ml squared. Mass times length squared times a 12th. Okay, so to find the moment of inertia around the end, well, this is going to be I-com plus mh squared. Well, this h here, it's pretty easy to see that the distance from the center of mass to the end of the pen is just the length of the pen over 2. It's just L over 2. So this just equals 1/12 ml squared plus m times L over 2 squared. So this is 1/12 ml squared plus 1/4 ml squared. A 12th plus a 4th, well, a 4th is 3/12, so 3/12 plus 1/12 is 4/12. I add all that up, and I find that the moment of inertia around the end of the pen is 1/3 ml squared. So that's how I can use the parallel axis theorem to find the moment of inertia around any other point on the pen. So for this class, to find the moment of inertia of any object, you can just look up the moment of inertia of the center of mass, around the center of mass of that object in this table from the book. This is in chapter 10. And then you can use the parallel axis theorem to calculate the moment of inertia around any other point. Let's start off with a conceptual question. A square plate can rotate around various axes as shown in the diagram at right. So these axes are all perpendicular to the plate, but they pass through various points on the plate. If omega equals 2 radians per second, for which axis of rotation is the kinetic energy the greatest? So which of these axes, which of these centers of rotation gives us the greatest kinetic energy of this plate? Okay, pause the video, take a minute to think about it, and come back when you think you have an answer. Okay, well, I'll remind you that the kinetic energy equals 1/2 I omega squared. Omega is the same for all of these. What changes is I. So the question is, for which of these axes is I the greatest? And then I'll remind you that you can use the parallel axis theorem, which says I equals ICOM plus mh squared to find the moment of inertia around any of these axes. So pause again, see if you can figure out which of these axes has the greatest moment of inertia, and then come back when you think you have an answer. Okay, well, we can eliminate C right away because H is 0 for C. C is the center of mass. C does pass through the center of mass. So the moment of inertia for C is just ICOM. So really the question is, which of these axes has the greatest H? The bigger H is, the bigger the moment of inertia is going to be, the bigger the kinetic energy is going to be. Well, let's say this plate has a side length L. Then this axis D here is going to have this H, axis C, axis B here is going to have this H, and axis A is going to have this H. So which of these is biggest? Well, this H for D, is the same as H for B. And these both just equal L over 2. They're both half the length, the side length of this square. H for A, well, this is a diagonal of this square. So this is going to be L, this is going to be root 2 over 2 times L. So it's going to be a little bit bigger than these. So HA is actually the biggest H, which means A, it's at the corner of this square, so it's the farthest from the center of mass, which means H is the biggest, which means I is the biggest for axis A, which means K is the biggest for axis A. So the right answer here is A, gives us the biggest kinetic energy. So if I rotate this plate around different axes, the kinetic energy can change depending on how far these axes are from the center of mass of the plate. Let's do an example of how we can use conservation of energy with our new formula for the kinetic energy of a rotating rigid body to solve problems that we couldn't have otherwise solved. So in this problem, a pulley has a radius r equals 10 centimeters and a mass m1 equals 2 kilograms. Two masses, m2 equals 1 kilogram and m3 equals 3 kilograms, are suspended from the pulley by a massless, extensionless rope. Treat the pulley as a uniform disk. What is the velocity of the masses after m3 has fallen through a height h equals 1 meter? Okay, so this problem is interesting. First of all, here we have a massive pulley. This pulley has a mass, m1 equals 2 kilograms. Previously in this class, we were only able to deal with massless pulleys, but now that we know how to calculate the kinetic energy of a rotating disk, we can actually start dealing with massive pulleys. Second of all, I want to think a little bit about why we can use conservation of energy at all. It's not obvious why we can. Well, let's think about the forces acting on this system. So our system is going to be these three masses, the pulley and the two hanging masses, plus the earth down here. The potential energy of the system involves the earth as well as all of this. Okay, so the only external force acting on the system, earth exerts gravitational forces, m2g, m3g, and m1g down on all of these. The only external force acting on this system is some force, let's call it, it's kind of like a normal force that's holding this pulley up. Now, this normal force here, although it is an external force acting on this system, it does not do any work. It doesn't change, it doesn't, because this pulley doesn't move. This pulley is fixed in place. So, we can say that the work done by external forces equals 0. So this is the change in mechanical energy of the system is 0. So we can just say, therefore, that remember, this change in mechanical energy equals the change in kinetic plus the change in potential energy. So we can expand out this kinetic energy and potential energy here. We can say that delta K1, that's the change in kinetic energy of the pulley, plus delta K2, it's the change in kinetic energy of M2, plus delta K3, the change in kinetic energy of K3, plus delta U1, plus delta U2, plus delta U3, the change in potential energy of all three objects, all adds up to 0. Okay, now these delta K's, well, when we start off, everything is at rest. So K1 initial is 0. So this is like K1 final minus K1 initial, but that's just 0. So these delta K's are all just K finals. This is plus K2 final plus K3 final. Okay, our delta U's. Well, this pulley doesn't move. Its height doesn't change. It's fixed in place. So the change in potential energy of this pulley is going to be 0. Now, since M3 is heavier than M2, M3 is going to go down, right? It's going to go down through some height delta H, which is 1 meter. If M3 goes down by 1 meter, this is an extensionless string. So that means M2 has to go up by 1 meter. So if this is 1 meter, this is 1 meter. Okay. So that means that that M2 gains potential energy. So we have plus M2 times delta H times G. Remember, the potential energy of a mass is mgh. M3 loses potential energy minus M3 delta H times G. This all adds up to 0. Okay, now we can start writing out these kinetic energies here. K1 final, well, the pulley isn't going to be moving, it's only going to be rotating. So at the end, this pulley is going to be rotating with some angular velocity, omega final. So this K1 final is going to be 1/2 I1, the moment of inertia of the pulley, times omega final squared. M2 is going to be moving up with some velocity, plus 1/2 M2 V final squared. So M2 is going to be moving up at the end with some velocity V final. But M3 is going to be moving down with the same velocity V final at the end. And since kinetic energy is just a scalar, it doesn't matter whether it's moving up or down, so this will be plus 1/2 M3 V final squared. And let's write this as, this equals M3 G delta H minus M2G delta H. I just moved those to the other side of the equation. Okay. Now I've written out my conservation of energy term equation, and I have all these terms. I'm trying to find V final. I have 2 V finals in here, but I also have an omega final, so I actually have 2 unknowns. Well, I actually have 3, because I also don't know I1, but real quick, it says treat this pulley as a uniform disk. So I know that I1, a uniform disk has a moment of inertia 1/2 M1 R squared. That's just a formula I can look up in the book, the moment of inertia of a uniform disk. Okay, so I1 equals 1/2 M1 R squared. But I still have these 2 unknowns. I don't know omega final and I don't know V final. So what I need to do is find some relationship between omega final and V final. Well, here's the thing. If this mass is moving down with a speed V final, then the string is moving down with the same speed, which means this point where the string attaches to the pulley is moving down with the speed V final. This point here is just a radius r from the center of rotation of the pulley. And we know that the tangential velocity of a point on a rotating object equals its angular velocity times the radius. So we know that this V final here, V final has to equal omega final times r. So if V final equals omega final times r, then we can say that omega final equals V final over r. And we can substitute these 2 equations back into our conservation of energy equation. So we get 1/2 of I1, which is 1/2 M1 R squared, times omega final, which is V final over R squared, plus 1/2 M2 V final squared, plus 1/2 M3 V final squared, equals M3. Let's write this side. I'm going to factor out the G delta H, so I can just write this as M3 minus M2 times G delta H. Okay, so over here now I'm going to factor V final out of this whole thing. I get V final squared times, well, look at this. R squared over R squared cancels, so I just get 1/4 M1 plus 1/2 M2 plus 1/2 M3. This equals M3 minus M2 times G delta H. So I can solve this for V final. I get V final equals the square root of M3 minus M2 over, let's write this as 1/2 m1 plus m2 plus m3, and then I'll go ahead and write this as times 2g delta h. So that's my formula here. And if I plug my numbers into this, I end up getting that this final velocity is 7.84 meters per second. Okay, so this is a really cool conservation of energy problem you can do once you know how to deal with rotational kinetic energy. And the key thing that this allows us to do is deal with massive pulleys, something we couldn't do before. But the trick to this problem was figuring out this relationship between the final velocity of these masses and the final angular velocity of the pulley. And to do that, we needed this equation here from rotational kinematics. Okay, that's all I have to say about rotational energy for now. In the next video, we'll come back and start looking at the rotational analog of force, which is called torque.